Good morning, everyone, and thank you for being here today. My name is Wang Zhiqiao, and I am honored to present my research title, Prediction and Analysis of Database in China, based on machine learning. This study is a result of months of hard work, combined clinical insights with modern AI approaches, and address the urgent challenge of database management in China. I hope this presentation will offer valuable perspectives on the role of data-driven healthcare in the age of machine learning. Here's a quick overview of what I will be covering in this presentation. First, I will introduce the background and objectives of my research to set the context. Then I will introduce the dataset I used and the preprocessing steps I took to ensure data quality. After that, I will look into 6 machine learning models applied, including their theoretical foundations and implementation strategies. I will then examine the experimental results and what insight I gained from data visualization. Finally, I will conclude with my key findings, elimination, and suggestion for future work. China has the world's highest number of diabetes patients with 141 million cases. Pre-diabetes affects around 500 million people, yet awareness remains low at just over 12%. Traditional screening methods often miss cases due to limited indicators and reliance on physician experience. Machine learning helps overcome these limitations by integrating complex data and modeling non-linear relationship. Our research has three main objectives: identify the best algorithm among 6 of medical data, determine the most impactful clinic features, and balance predictive accuracy with interpretability. For research objectives and implications, research objectives from 3 aspects. Number one, which of the 6 mainstream algorithms is best suited for structured medical data? Number two, which clinical indicators contribute the most diabetes risk? Number three, how to balance model accuracy and clinical interpretability. For research implications, it provides technical support for early clinic screening to improve the early detection rate of diabetes and cellular picture effects, provide data support for precision medicine and optimize personalized medical solutions, provide sound scientific evidence to advance diabetes prevention and management literal transformation. For this study, we plan to study these steps to find the most suitable machine learning model. The solution proceeded in this study follows the following process: data collection, data processing, model training, performance evaluation, model training, and final model employment. This series of steps is shown in the right, which aims to achieve accurate prediction of diabetes risk and provide data-driven decision support for clinical early screening to public health intervention. Earlier study relied on logistic regression, which is simple but limited in capturing complex patterns. More recent models like random forest have improved performance but often lack large of diversity datasets. Our study systematically compressed 6 algorithms across a robust pipeline of pre-processing, cross-validation, and evaluation. This ensures more reliable and generalizable results, helping to push the boundary of database prediction research. For a list of variables, the dataset contains 17 characteristics, including demographic information, psychological indicators, biochemical indicators, medical history, etc., covering age, pregnancy, blood glucose, BMI, family history, etc. There were no missing values in the dataset, but there were outliers, such as 1.2% of the records with blood glucose equal 0 and the extreme BMI of 49.66, which were processed by mean, feeling, and IQR methods. The technology chain is raw data, data cleaning, feature engineering, dataset partitioning. We use boxplot combined with the interquartile range method to detect that processing possible outliers in the data. Outliers are defined as extreme observation that exceeded the normal distribution range, which may lead to model deviation if not proceed. The specific approach is to calculate the upper and lower threshold of each feature and replace the abnormal data that exceeds the threshold with the corresponding boundary value to ensure the robustness of the data and the stability of the training process. For data visualization as a tool to convey information about data and images effectively through means of graphical representations. Common visualization to be executed in Python includes line chart, bar chart, scalpel, hotmap, and others. The visualization could be done with the help of different libraries input into Python, such as Matplotlib and Seaborn. In the study, 6 supervised learning models will be used to predict database risk, including logistic regression as a classic learner model, k-nearest neighbors as a distance-based normometric model, decision tree and random forest as a representative tree model. Support vector machine for high-dimensional data segment and Naive-Bayes as a probabilistic model. We use four-case metrics: accuracy, precision, recall, and F1 score. While accuracy shows overall correctness, precision and recall helps evaluate how well the model identifies true positive cases. The F1 score combines both, making it especially valuable in healthcare, where both false positives and false negatives can impact patient outcomes. This metric ensures our model was not only statistically accurate but also clinically meaningful. Among all models, random forest performed best with 99.97% accuracy, 99.92% precision, 100% recall, and an F1 score of 0.996. Logistic regression followed with 98.78% accuracy and only 0.4 seconds of training time, making it efficient and interpretable. Support vector matching also showed strong performance with 98.56% accuracy and an F1 score of 0.9787. Overall, random forest offers the best balance between predictive power and generalizability. We found key trends from visualization. For instance, people over 50 and have 25.5% database that of those under 30.82% of individuals with MBI over 28 and high blood glucose. We also built a dynamic dashboard for real-time risk scoring and tailored health suggestions, enabling fast and user-friendly clinical assignments. Finally, for key findings, algorithm selection: random forest is the optimal model taking into account both accuracy and generalization ability. Logistic regression is suitable for linear scenario. Future insight, metabolic, metric, blood glucose, BMI are the co-drivers. For study elimination, data level, only a single group of people, lack of ethnic diversity. Dynamic data was not included. Model type level, random forest is not explanatory enough. Deep learning is not exploited. In short term, I aim to collect more diverse data across regions in China and develop a mobile app with our model embedded. In the long term, I plan to integrate genomic data and connect with hospital system for real-time decision support in clinics. Thank you very much for your attention.